All right, so by these slides, we went back to the original definition of a phasor, right? We show the phasor is actually a way to simplify the notation for instantaneous voltage or current instead of writing the accurate waveform. We can just only capture the magnitude and angle. When we develop the long line models, we are able to calculate the voltage at any distance to the receiving end. If we use the receiving end as the coordinate origin, so we'll have this function to describe how the voltage will vary along the transmission line. Then we can go back to the instantaneous voltage, but now the instantaneous voltage will be a function of both time and distance. So it'll be a t and x. So when we describe any continuous variables changing with x and t, very likely this variable can be represented by some wave function, which is also true for this case. So we construct these functions which have two components. So first component, so the moving direction is from the left to right, from the sending end to the receiving end. The other function is a wave moving from the right to the left. We call the first wave as incident wave because the amplitude is decreasing from the left to right. And the other wave will be the reflective wave. So it's moving from the right to left. Because if we know the active power is sent from left to right, from the sending end to the receiving end. So the right wave will always bigger than the blue wave. So which is like you send some energy from the left to right, and some of the energy will be reflected back. So that's why we call the right wave as incident wave, the blue wave as reflective wave. And both waves are actually moving at the same speed. So we're going to prove in the following slides. So we want to answer the question, what are those waves? Okay, let's pick the blue wave as one example. Definitely you can work on the right wave as well. For the blue wave, it's a function of both time and x, right? The distance to the receiving end. It involves some parameters. For instance, alpha and alpha beta. Alpha beta is the real part, imaginary part of gamma. Gamma is defined to be the square root of the product of z and y. Z is the impedance per unit length. Y is the admittance per unit length. Also, we also introduced another index, which is ZC, called the surge impedance. Surge impedance is defined to be the square root of the Z divided by Y. Okay, so we keep those in mind. And then we try to figure out the moving speed of this wave and probably also the wavelength as well. And we can think about the analogy. If we're able to see it on the wave moving together, so what we're looking at the wave will have the exactly same phase, right? If you sit on the peak, you'll be always sit on the same peak if you're moving at the same speed of the wave. Okay, so which means to calculate the speed, you need to assume you are sitting on the wave and with the total phase. So this one is constant. So the A2 only depend on the is constant for this case, like only depend on the line parameters and the voltage and current on the receiving end. So we expect this part. So if this phase is constant, so this one will be equal to a constant number. We don't worry about what that value is. Let's take a time derivative of this equation on both sides. When you take time derivative, you will this t will be gone. And this x will become I star, and this constant will become 0. So you'll have an expression which is omega minus beta I star equals 0. So I star will tell you the speed of the wave. Okay, so you can directly calculate the moving speed of the wave and also the wavelength. So the speed will be the time derivative of x. So from this equation, so that exactly omega divided by beta. Okay, wavelength will be equal to the speed divided by frequency, or speed multiplied by the time of one cycle. So that will be omega divided by f will be 2 pi. So wavelength will be 2 pi divided by beta. Okay. And so what are those values? Let's consider a simpler case for a line without any loss. So in this case, alpha will be 0. So beta will be omega times square root of L times C. Okay, so we just plug in this one to both equations. So let's see what we get. So the speed is equal to 1 over square root of L times C. Okay, lambda is definitely speed divided by f. So you will see f on the denominator. So let's go back to the formulas calculating the L and the C from the line parameter sections. So we know the L and the C only depend on geometry of the line, not the material of the line. So if we know the geometric mean distance, which is if a three-phase line, we know the separation, the distance between any two faces, so we can calculate a GMD. If we know the radius of the conductor, even they may have many conductors together make a bundle, so we still can calculate geometric mean radius. So when you calculate geometric mean radius for inductance and capacitance, you will use a slightly different formula, but they can be very close. But anyway, so L and C only depend on geometry of the conductor of the line, not the material. Okay. And the two equations involve, for instance, the mu0 in the equation of L, the mu0 is permeability. And the capacitance equation involve epsilon zero. Epsilon zero is permittivity. Okay, mu0 is defined exactly 4 pi times 10 to the -7. So let's see if we plug in those two formulas into the speed and the wavelength equation. Let's see what we get. For the speed, we plug in L and C, we'll get this expression. So for this item, this is like coefficient I color in the magenta color. So what is this one? This one is exactly C. The speed of the light in outer space, in free space. That's exactly equal. Why? Because epsilon zero is defined by this formula. It's not measured form. It's not estimated or measured parameter. It's actually defined parameter. So if we know C, and we define mu0 as 4 pi, so now you see why this one is like 4 pi. And epsilon zero will be calculated directly from here. And the value will be about this value. So we mentioned this value before. So which means this coefficient is exactly the speed of light. And how about the next item? The next item, that's roughly 1, because GMR-C and GMR-L are different. But the only difference about the inside of the conductor, right? Remembering, so the key difference between the electric field and magnetic field can stay inside of the conductor, but electric field can only stay outside of conductor. So which means, so when we calculate the geometric mean radius for capacitance and for inductance, for capacitance, we have to exclude the inside of the conductor. Okay, so if you think about the conductor can be very, so the GMD can be very large, much bigger than GMR-C or GMR-L. So eventually, this one will be very close to 1. Because keep in mind how to, this formula, I mean, everything here will actually equal to log GMD minus log GMRC C, right? Divided by log GMD minus log GMRL. So if GMD is much bigger than either GMRC or GMRL, so those two items can be ignored on both numerator and denominator. So eventually this one is extremely close to 1. If you consider many conductors.
Sorry, I kind of forgot what is L and C. Did you explain them a little bit?
GMRL, GMRC are both the geometric mean radius. So when you calculate GMRC to calculate the capacitance, in the formula, if you use a radius, you use actual radius. When you calculate GMRL, so you use the equivalent radius, which is called R prime or ds. So that's about the 78% of the actual radius. So go back to this example in the section number 4. So if you consider two bundled three-phase lines having GMD 44 feet, and GMRL is 0.22 feet, and GMRC is 0.24 to 25 feet. And so if you plug in those values into this formula, that factor is 0.99. So which means that's a 99% of speed of light. So if you have the electromagnetic wave moving inside of this transmission line, so you measure the speed of the wave, that's 99% of the speed of light. Okay, so we know, so speed of light is defined value. It's not measured value, it's defined value. It's exactly 299 million, then 792,458, round exactly the value, okay? So which is about 300 million meter per second, roughly. So that means the wavelength will be the speed divided by frequency, which is 5,000 kilometer. So if you operate a 60 Hertz power system, the wavelength of the transmission line will opt out for the wave propagation. The wavelength is always around 5,000 kilometer. If you operate 50 Hertz system, so this one will become 6,000 kilometer. So shortly, I will show why the wavelengths matter, because wavelengths really tell you the theoretical boundary for you to deliver the energy through a single transmission line. So why do we have so many towers, right, to connect? If you want to deliver the electricity over hundreds of thousands of miles, it's not possible to build a single transmission line. It's neither possible or efficient. Okay, so now you can understand why beta is always 0.0013, no matter what line, what voltage. As long as you operate the system at 60 Hertz, that's always 2 pi divided by lambda. So lambda is always around 5,000 kilometer. So beta is very close to 0.0013. So it's fine you use this value for approximate estimation, as it doesn't depend on the length of line or the voltage of the line or size of conductor. It's very close to this value. Yeah, GMR, the definition is here. So depend on you want to calculate GMRL or C, you need to choose to use for the DII here with both subscripts the same. So either use actual radius or 78% of the radius. So how much difference can that generate? So when n is very large, if we utilize another example from section 4, if it's a conductor with a nice strength, the GMRC divided by GMRL is 1.04. So we only have 4% of difference for such transmission line. So 4% difference, go back to this formula, that's make it almost like same one. That's 4% difference can be ignored, because GMD is much bigger than GMR. So then we can immediately get a few useful formula to estimate the surge impedance. So surge impedance will be is equal to the square root of L by C, and so we can make a denominator be the square root of LC, because purpose is we want to involve the speed of light. So finally we can use the speed of light multiplied by the inductance to give you estimate of the surge impedance, or you use 1 divided by speed of light and the capacitance to give you the estimate. So which will be very good estimate and easy to calculate. Okay, any question here? So electricity in transmission line is delivered through such an electromagnetic wave moving at around the speed of light, right? The similar to the speed of light in the outer space, very closely. So there's a example 5.6, and so we can just do some calculation. So this example focus on calculating a number of the capacities, loadability, and the limits of power for the line. So if we have a three-phase line sending which is it's a 700 megawatt power transmitted to a substation at a distance of 315 kilometer. So if we know some per unit value for the source voltage and the load voltage is slightly lower, and the wavelength is 5,000 kilometer because it's a 60 hertz system. Surge impedance, if it's 320 ohm, delta is actually the angle separation between the source and the load. So using those parameters, we want to estimate the nominal voltage level for the line. And then we want to calculate theoretical power limit, and also that can be transferred by the line. Okay, so basically we're going to utilize those two formulas. The first formula is about IT power, and so this right coefficient is actually just the theoretical limit. Okay. Surge impedance can be calculated based on the rated voltage divided by the surge impedance. So that will give you the surge impedance load. So first, beta L is defined to be it's actually 2 pi divided by lambda multiplied by the length of the line. So if we already know lambda, so we can just plug in the lambda. So this 360 is just the 2 pi. It's just 2 pi in degree, because here we want to get the angle in degrees, which will be the 22.68 degree. So if you want to try to calculate beta is defined to be 2 pi divided by lambda, which is 0.001256 per kilometer. So it's still very close to 0.0013. Okay, so utilizing this formula, so we can calculate SIL, the surge impedance load, because that's only unknown here. So the answer is around 500 megawatt. And using this formula, since so we want to calculate actually the line-to-line voltage here. So that's a 400 kilovolt. Okay, so for this line delivering 700 megawatt power, so it's better to have a 400 kilovolt at the voltage level. So theoretical limit will be this item. So we already have everything, right? You just plug in the value, it will give you slightly higher 1100 megawatt active power. Definitely, you can also calculate directly from here. So because this one is same at the theoretical limit, you just need to utilize the 700 divided by this sine angle. So that gives you exactly the same answer. So this is an example. All right, so let's compare those limits we calculated about the transmission line. So let's study the same transmission line. So here, if we assume the rated voltage is about 400 kilometer, okay, and the the current limit is 3 Ka, and the surge impedance calculated around 500 megawatt. And you know, because theoretical limit is very high, theoretical limit assume the angle can reach 90 degree, but which never happened. Let's go back to this formula about theoretical limit. So the thermal limit defined to be just the apparent power when the current is at the limit, the thermal limit, and multiplied by the line-to-line rated voltage. So this is the thermal limit. And theoretical limit is when the angle take a 90 degree, so which is here. But usually it will never reach 90 degree. So a more practical limit will assume just 30 degree as the largest angle. So 30 degree sine 30 degree will give you half. If here is 1, this is half of the theoretical limit. So usually we can use half theoretical limit as the practical limit. So that slide just compare those limits on this example. So if you calculate the thermal limit, which is around 2,000 megawatt. For theoretical limit, we get a formula because we don't know the length. Let's just assume the length can vary. So the theoretical limit will be a function of the transmission line L. So if you plug in the L, you can calculate theoretical limit. But from here, we can somehow get, if the line is very long, the theoretical limit will be decreased. So when L is 0, it's very short. The theoretical limit can be infinite, can go to infinite, right? If the L is 0, so the denominator becomes 0. So this one, the P35 mass can go to infinite. Yeah, let's verify those gases to draw the curves. So the first curve is the green is actually the surge impedance load. That's around 500 megawatt. So the X here is just the length of the line. So if we can vary the length of line from 0 to the value 315 kilometer is the length of the line given by that example. Let's just assume the length can vary from 0 to 315. So surge impedance load will be flat, will be exactly a constant value. And thermal limit is also constant. It's around 2,000. That's thermal limit. It's a blue line. And the theoretical limit is this one. So if you plug in L equals 0, so this will give you infinite. This will give you infinite. But when you have length of 315, this will give you the value we calculated from that example, right? Which is between 1,000 and slightly higher 1,000 megawatt. A practical limit, because we assume 30 degrees, sine 30 degree will give you half of the theoretical limit. So the practical limit is the curve always taking the half of the value of the right curve. So now you can see the relationship. The surge impedance load is actually the ideal load. So if you operate the line, delivering power exactly equal to surge impedance load, you have the minimal operation challenge. Okay, the voltage everywhere will be same. Power factor along the line will be same. So that's ideal load. But usually, our load is most of the time is higher, can be higher than surge impedance load. But we still need to pay attention to the margin between this load and the practical load. We don't want the line to be overloaded. Even you can slightly over the practical line loadability, but you should never go to the either thermal limit or the theoretical limit. So that's a line up to 315 kilometer. So if we continue drawing those curves until, for instance, 5,000 kilometers is actually the wavelength of the line for 60 Hz system. And eventually you'll see the theoretical limit and practical limit will keep decreasing. Eventually, both curves can be under the surge impedance load. Because you can tell from this value, right? So this value is lower than a certain impedance load. So when the denominator become 1, so when you take a 90 degree, sine 90 degree, that make the theoretical limit the minimum. So this point is actually a quarter of the wavelength, because a wavelength is 5,000. So this point is about a quarter of the wavelength. So at a quarter of wavelength, the theoretical limit is even lower than the third impedance. So this explains why you cannot have very long line, right? And if you make a line even longer, okay, what if I only deliver very small amount of power, not even higher than certain impedance load? Would that be safe? No, eventually when you reach the half of the wavelength, which is 2,500 kilometer, so you see the limit become negative. So theoretically speaking, you're unable to deliver electricity by single line, which is longer than half of the wavelength. So that's why the wavelength is very good indicator on how much margin you have utilized. If the longer the line, the smaller margin you have to further deliver over the distance. Okay, does this make sense? Okay, any question? All right, so yeah, so this is half. Yeah, this point is a quarter of the wavelength. So you need to expect to have the line shorter than, at least shorter than a quarter of a wavelength. Yeah, that's already very long. It's already longer than 1,000 kilometers. So that's not the, in real world, it's not a very practical length of the line. All right, so the only last section, small section, will be talking about how to utilize the capacitors and reactor to compensate a line if the line doesn't have perfect voltage along the line. So if the line is not supplying the load at a certain impedance load, so the line load can be higher. If it's higher, so you may have under voltage problem. So which means near the load, the voltage can be lower than the source. If the load is lower than certain impedance load, you will have higher over voltage problem. So the voltage on the load will be higher than the source. But you need to maintain, it doesn't matter it's under or over, but you need to maintain within the limit. So those capacitors and reactor will give you some compensation for the violation of the voltage issue. So the capacitors and the reactors can be designed as either permanent fixed components of the system, or they can switch into an out of service using like circuit breaker switches. There are full combination of ways to utilize capacitor or reactors, depending on how they are connected to a system. So they can be connected with a load in series, in parallel, and also it can be reactor or capacitor, so there will be a full combination. So for shunt capacitors, so they can inject reactive power at the point of connection and just support the voltage. Shunt reactor can absorb reactive power at the point of connection and lower the voltage. Series capacitor, they will be connected in series with the load. It actually can cancel some inductive reactance, so which give you the effect of making the path impedance shorter, smaller. So that can improve the stability and reduce losses of line. A series reactor can increase the impedance of line. So you may wonder, under what cases I want to increase the impedance of line? Because, for instance, if there's some short circuit, the short circuit will increase the fault current. So if you increase the impedance, the fault current will be limited. Okay, so series reactor is mainly utilized to limit the fault current or reduce power oscillation. It's not mainly to support voltage. So here we focus on the first three ways. Let's compare the two capacitors. One is connected as a shunt capacitor. The other is connected as series capacitor. So shunt capacitor will be so this is a load will be connected to the two terminal of the load. And series capacitor will be added into the transmission line. Okay, so what are the differences? So we know the capacitor, a capacitor is always a reactive source, no matter how it's connected to the system. So no matter it's connected to the load side or in the middle of the transmission line, so it always provide reactive power. It's just a matter of how the power is provided and calculated. So for a shunt capacitor, so if we assume the capacitance is this XC SH, that's for shunt, it can be connected directly to a bus bar or tertiary winding of a transformer, but typically just near the load. The capacitor bank may look like this picture, but the connection can be either as a shunt connection or series connection. So if you calculate how much reactive power provided by this shunt capacitor, so we'll need to utilize this voltage, right? First is 3 times the voltage magnitude squared divided by the capacitive reactance. So that's a Q. Advantage is the cost is low. It's very flexible to install and operate. So you just play the substation there next to the load. So load here can be one city. So if you're able to drive along the Palisibia way, so you can see there's one capacitor bank there. Okay. So disadvantage is the Q depend on the voltage. The Q proportional to the voltage squared. So which means when the voltage is lower, the Q also decreases. So just give you one example. So if you need to install a capacitor bank, and based on your estimation, you have shortage of around 20 to 25 megawatt reactive power shortage. Okay, so you go to the manufacturer, you find there's a shunt capacitor for the capacity of 25 megawatt, so which is good, right, to meet your requirement. But they show you need to install this capacitor bank at 115 kV. So if you install this bank at 115 kV, operate at that voltage, you're going to get that 25 megawatt reactive power for sure. Then you install there. But when you need that capacitor bank, for instance, your voltage drop to 109, which is 95% of the nominal voltage. So you realize, okay, so if I allow the voltage to decline further, that will the violation will happen. So that will be lower than 95%. So I want to switch in this capacitor bank. So if you switch in this capacitor bank based on this voltage, if the resulting voltage is still around 95%, so your reactive power is 25 multiplied by the voltage squared, which will give you only 90% of what is on the plate, right? Because that reactive power depends on voltage. So at the end, you only get 90% of rated voltage. So which means you need to buy the capacitor bank slightly higher than your requirement, because you need to forecast how much voltage can decline. And the Q is proportional to the voltage squared. If the voltage decline, the Q will decline as a quadratic function. So that's a drawback. Let's talk about the series capacitor. So for series capacitor, the Q is also proportional to the it's also changing, but proportional to the current square. It doesn't depend on the voltage on the load. So if you calculate the IT power, if you add the capacitor there, it will cancel the reactance, the inductive reactance of your line to make the denominator smaller. So eventually this one will decrease and the IT power can increase. So one advantage of adding the series capacitor also increase the capacity of the theoretical capacity of the line, because this is like theoretical power limit. So usually we use percentage compensation to indicate the size of the capacitance relative to the line impedance. Okay, so line impedance, if we ignore the resistance, so it's roughly the X prime. XC SR is the capacitive reactance of the capacitor. So this ratio multiplied by 100%, that give you a percentage compensation. So the advantage is self-regulating. Self-regulating means it doesn't depend on voltage, but it depends on current. So when your system needs a lot of reactive power, the current usually is also high. That actually make this capacitor in the series connection to provide more reactive power under the heavily loaded condition. But disadvantage is it will have series connection with the inductance. So whenever you connect a capacitor directly to an inductance, you will cause some resonance. So we'll create the resonant circuit. So if you have capacitance connected with the inductance, so this C, this is L. So for such circuit, if you can inject some current, that would be resonating there at a certain frequency. So that frequency, that resonating frequency can be calculated by this formula because originally defined, the resonance frequency is defined to be 1 over pi multiplied by square root of 1 over the product of L and C. So then if you add the synchronous frequency, which is 60 hertz here, so you can get this formula. So that tell you what the resonant frequency is. So if the 60 hertz, the synchronous frequency is 60 hertz, so you will get the resonating frequency. So for instance, for 60 hertz, if we do a 25% of compensation, so if this ratio is 25%, which means the capacitive reactance will cancel 25% of the total line impedance, then the resonance frequency will be 30 hertz. So it will introduce subsynchronous resonance. So this become an increasing challenge to operator when you integrate a lot of renewables, and sometimes you need to add compensation to the long transmission line, so you will introduce subsynchronous resonance. So for instance, if you have wind farms far away from your city, but you want to deliver electricity over long distance, and you want to make the line shorter by adding the series capacitance to cancel some line impedance, you will introduce some subsynchronous resonance. Okay, so let's talk about the shunt reactor. The shunt reactor is needed when you have load, but the load is just open the circuit, and the voltage on the receiving end will increase. If the line is very long, this voltage can be very high. Then you need to switch in a shunt reactor. Let the shunt reactor behave as a new load to limit the voltage. So we know the line current at the receiving end now become just voltage divided by the reactance of the reactor. We want to get the idea on how the voltage and the current distributed along the line when we open the circuit and switch in the shunt reactor, and we want to see how the voltage can be limited by the shunt reactor, and how the current can change. So we still go back to the original formula. So this one tell you how the source voltage change with the low voltage and current. So we plug in this current here because we want to generate the formula only depend on the low voltage. So you see, so this J and this J will be canceled. So finally, the source voltage will be equal to everything in such parentheses as factor multiplying the load voltage. Because the J has been canceled, so this factor is completely real. It's a real number. if it's a real number, it doesn't change the angle. So which means the source voltage and the load voltage are completely in phase, parallel. So we move further. So that makes sense because right now we don't deliver any active power over the line. So in order to deliver active power over the transmission line, you need to create the angle difference between the two ends. But right now there's no active power. So the VS and VR, they can be parallel. They have the same phase. So if we further require the load voltage to be same as source voltage, so if a source voltage is 1 per unit and load voltage always also exactly 1 per unit, then we'll need this factor to be exactly 1. Okay, so we need to have this one hold, which means for this factor, it can be solved as this one, and this is actually equal to a tangent half of the beta L as angle. And then we go to the current formula. The source current is equal to expression about the load voltage and current. And in this case, we plug in the formula for VR. We want to get the expression only about current. So we also have another factor multiplying the load current. And this factor is always also real. So we know the source current and the load current also in the same phase. There's no phase difference. You can quickly prove this factor is actually exactly -1. What you need to do is just need to plug in, because here we know the ZC divided by the writer in readings. So we plug. So here you have a ZC, you have another SLC. So you actually can plug in that one here. It's not hard. You can prove this one is -1. So the source current will be a negative load current. So this one means the source is sending current from the left, and the load is sending the same current back. That is S. So the both ends are sending the same current, but in the opposite direction. Eventually, they are going to merge at the middle point. So at the middle point, the current is 0. Okay, so if you measure the current at either end, you will get the magnitude same as the source current. But when you move further to the middle point, the current will decline, finally will become 0. So what does this one mean? So if you further use this formula, but now you instead of considering the full length of line, you consider half of the lines. And you do some simplification. So this tangent half of beta L is come from ZC divided by XL. So this factor is equal to 1 over cosine half of a beta L. So this one is bigger than VR. Also bigger than VS, because we already make a VR VS be equal. So at the midpoint of the line, the voltage is higher than both ends of the voltage on both ends. On the textbook, there's a figure to show using the example, the same example of the line. So you can tell, so if you open the circuit at the low side without switching that shunt writer, the voltage will go up, right? From 500 kV to be close to 540 kV. 540 kV is around like 8% higher, so that's too high. Usually we use 5% at the threshold. So this has violated the voltage limit. So you want to switch in the shunt director. And we can make the load voltage to be set exactly at 500. But that will increase the voltage at midpoint by about 10 kV. Okay, so increase about the 2%. All right, so that's the last thing we need to know about compensation. I put this final slides, which is not required by any homework or test. Just give you an idea on what the state-of-the-art technology is for the line compensation. So this technology is called static VAR compensator. Static VAR compensator is just a bunch of capacitors, resistors, which can more flexibly switch in and out. Static means there's no generator at all, but they can provide either provide or consume ready power as a generator. So you usually have a number of components. First, you need to have a control system. The control system need to sense the voltage, either remote voltage or local voltage, to decide whether you want to switch in capacitor or switch out capacitor or adjust any reactor. And the switch actually was implemented by power electronics arrestor, so they can quickly adjust the number of reactor and capacitor at any time. And so those components just similar to the capacitor bank, right? You have either reactor, capacitor. You can decide which one to be connected at any point. So because it involves power electronics, that can introduce some harmonic. So you also have like a high pass filter to filter out fifths, sevenths, or up to 13th order harmonic. TCR is especially for sequencer control reactor. TIC is for sequencer switch capacitor. Okay. So if the voltage deviates from the target, and this control system will decide how much VAR will be needed. It could be a positive VAR or negative VAR. If the voltage is lower, so you need to switch in capacitor or switch out reactor. If it's higher, you need to switch out capacitor. So this is the last slide of this section. All right, so next week we'll move to the power flow, the really important section.